Hi everyone. I hope you've had a good first day here at JFocus and is ready for one last session. We're going to talk about geographical AI and specifically the talk from pixels to pattern, how to handle too much training data. So hearing AI and too much training data together might sound a bit weird, because usually when working with AI and machine learning, you have the opposite problem. You don't have enough training data, so you need to do all of these tricks in order to make the most out of your data. With some of the projects that we've been working on, we actually have so much data that it's more a case of finding a good way to select what part of our data we want to use for training. So that's what this talk is about. But what you'll actually learn during this talk is how to build illegally without getting detected by an AI. And soon you'll understand why. So first, let's introduce ourselves. My name is Mathilde. I work as the head of AI at Norkart, and with me I have my colleague.
Yes, my name is Malte. I'm a machine learning engineer. I'm quite new at Norkart, started in August last year, but I've been doing various machine learning projects the last 7 years.
Yes, so Norkart can be translated into North Map. So we're a Norwegian software company with around 230 employees. And we make all types of different software and applications that make use of geographical information in some way. So the AI team at Norkart, our goal is to figure out how machine learning and AI can work together with our geographical data to improve our products or to improve the data itself. So there's a lot of talk about AI, and there are many definitions of what AI really is. And this one is my favorite. AI is just what people call stuff that feels magical or not possible with computers. And when it becomes possible, we stop calling it AI. So I heard this on a podcast called Hard Fork, and I think this is actually pretty fitting to how many people do perceive AI. I mean, it's called artificial intelligence. It feels like something that should be really impressive. It shouldn't really be possible to do with a computer. And as AI becomes better, our interpretation or feeling of what AI is also shifting. So it's very important to keep in mind that AI is just a tool that we use in order to find some kind of system in our data. So with traditional programming, you have some input data and a program, you run it on a computer, and you get some output. But with machine learning, you turn it around. So you have some input data and some corresponding output data, and you use your computer to create a program that finds the correspondence between the input data and the output data. But we're going to talk about our project, so Malte,
yes,
can continue.
Thank you. So the project we'll talk about today is about automatic mapping, and more specifically how we can map buildings. So how are buildings in maps actually created? So in Norway, at least, there's two ways. I assume it's kind of similar in Sweden and other countries. The first way is whenever a change is made to an existing building or you want to build a whole new building, these changes are notified to the municipality. For instance, if you want to build a building on your property, you need to apply for a building permit, which gives the municipality the chance to update its data and therefore update the map. Another thing, some buildings you don't actually require you to apply for a permit, but you can just send in a notification at the end of the building process. But some people, they don't apply for this permit, and some people, they forget to turn in this notice, which leads to outdated maps. This brings us to the second way that you can update maps, which is by manually construct maps from aerial images. So, for instance, we can look at this one. This is an aerial image. After all of the municipalities, they're continuously taking these images over all of Norway. And after they take these images, they can order this analysis where people go through these images manually, trying to detect changes from this image to the maps. And if they find any changes, they can then update the maps. So for instance, this image can become a map looking something like this. So why is it important that we have the correct building data? Well, there's numerous reasons, and we're just going to list a few ones here. The first one is because of land use. We want to know what's built where in case of disaster, in case of maintenance, and just in general in case of the citizens, in what the citizens needs. You also want correct building data because of taxes. In Norway, at least, your taxes is based on the properties or the buildings on your property that you own. You also want to know what's built where because of planning the infrastructure around your properties. And when you sell or buy a property, you want to make sure that this data is correct so you get what you're paying for. Yes, so however, this analysis that I mentioned is actually quite difficult to do because imagine looking at this picture and then you have to find out if a new building has popped up or if there's any extension to a building. So we wanted to see if there's a way of automating this. So maybe we could use AI here because AI is really good at image analysis and it can analyze large areas really fast, and training data can be created from already existing data. So it sounds like a really good fit. So a little bit about how we automatically create the training data. At Norkart, we have aerial images of all of Norway. And what we do is that we create small tiles, 512 by 512 pixels, which seems like a reasonable size for a machine learning model to work with. We also have existing building data. And what we do is that we extract the building data corresponding to the aerial image. And then we get, for that image, if there is a building, for each pixels, we get if there's a building there or not. So it looks something like this. And then when we put these images on top of each other, we can see that they correspond pretty well. So to train an AI to detect building, we need some houses to train on. And if we train an AI on these images, the AI will then learn the features of the houses here, and that will become the definition for the AI of what a building is. But I'm wondering, does anyone here see any problems with this selection of houses? Yeah, all the roofs are black. That is completely correct. Anyone else? Shadows, yes. There are there are just a few shadows, no shades on top of the roofs, yes. And these are all definitely correct. So you want to kind of diversify this a bit more. You want the roofs to be in different shapes. You want the roofs to be in different colors. You want the surroundings to be different. You want some grass, some concrete, and so on. And you also need more shadows that overlaps with the roofs as well, and not only the surroundings. And at the end, what we want to do is that we want to give the model one of these tiles. And we want the model then to predict if there's buildings or not. And then it goes through every pixel, and it will give a probability of how sure it is if there's a building there or not. Yes, and an important detail about this is that the images are georeferenced. And that means that we know the bottom left corner XY coordinate, and we know the size of the image, and we know the size of each pixels, which means that we can calculate where in the real world this image is taken, and therefore we can also calculate where in the real world these buildings are located.
Okay, so we've been working with these types of models for several years now, and it's been a long journey. A lot has happened within AI, and also with how we use our training data. And there are really two parts to this project. One is the training data and how we train our models, and the other one is the type of models that we're using to solve this problem. And we've implemented many different models and tested a lot of different ones. But the really big performance leaps have been due to changes in training data and how we train our models. So this talk is focused only on the training data part. So let's start at the beginning. As Malte said, we have aerial images for all of Norway. We have building data for all of Norway, and we can create training data automatically. So that means that we can just create training data for all of Norway. Well, that would give us 146 million tiles and a total of 8.6 terabytes of data. This might not sound like that much data, but when you're working with a proof of concept project like this, you don't want to handle this much data. It's costly, and we wanted to train on the machine learning computer that we had in our office, which wasn't that powerful. And if we were to train on our machine with this amount of data, it would have taken us 1,703 hours for the model to run just one epoch, meaning the model sees the data just once. And with machine learning, you usually want to let the model see the data several times in order to learn from that data. So if we were to run 20 epochs, it would take us 1,419 days. Not an ideal solution. So if this was our only problem, we could have solved it by moving things into the cloud, pay for more compute power. But we had a different problem as well with our data. The data is really unbalanced if we use data for all of Norway. And what do I mean by this? Well, if we were to look at random tiles across Norway, what would we see? Nature, nature, nature. One building, some ocean, and more nature. In fact, only 1.7% of Norway is actually covered by buildings. The rest is areas like this. So if we were to train for the 1,419 days, be super excited to see the result, we would get a model that just said that nothing is building. It would be correct 98.3% of the time, which is really good results for an AI. The AI would be really happy, and we would feel pretty stupid. So instead, we decided to use just a part of Norway for our training data. So we chose a pretty big area in the south of Norway where we know there are lots of buildings and lots of different buildings and nature. And we decided to include a criteria. So we only want to create training data for tiles where there is at least 5% buildings, which means that this tile would be a part of our dataset while this one would be excluded. So we have aerial images in a web map server and building data in a Postgres server. And these are servers or databases that Norkart already have, and it's used across many different projects. So we can just connect to those existing databases. And then we can look through the sample space that we chose and look at every single tile within that area. And if there is at least 5% buildings, we create the data sample. This is then downloaded into our training data set, which is then split into 3 parts: training, validation, and test. When working with machine learning, it's very important to keep some of your training data for testing and validation. So after running this process and creating all the training data, we can then start training our model. And the model gets to see all the training data and adjust its parameters and try to figure out what is the common visual thing between all of these buildings in the training data set. And it then runs validation, sees how it performs, and it keeps doing this in iteration for as many epochs as the model keeps learning new things.
Yes. So let's look at some of the fun parts. Let's look at some results for this proof of concept. So this is an image. We can see some examples of detected buildings. The buildings are in pink. And if we zoom in a little bit, we can see that it works pretty well. We can see that it has learned what is a building and what is not a building, but it struggles a little bit with the exact shapes. And that's because it's predicting for each pixel, and therefore the corners and the edges are a little bit more difficult for the AI to figure out. For our case, though, that doesn't really matter that much, because we just want to know if there's a building there or not, so that someone can take care of it for us. All right, so the results were pretty good. So we created a new test area in Kristiansand in Norway. And the result from this test area was that we found 93.6% of the buildings, and we only had 23 buildings that were false detections. So after running on this test area, we continued, And what we could now do is that we could now take this AI analysis and we could run it on big areas for whole municipalities in Norway. This would give, we could then compare these predictions to the existing buildings in the maps. And this would give us the suggestions of new buildings and new building extensions. We then created a web application where the municipality could then assess these predictions if they're right or wrong. And after they manually go through these predictions, we actually end up with some actually new buildings and extensions that were found. And then you could use these new buildings to update the maps. All right, so this is how the web application looks like. The municipality works in here and they can scroll up and down to see all the predictions. And if we click on one prediction, this is how one prediction detail looks like. So in the top left corner, we have the newest aerial image. And in red, there's the prediction for the model that there's a building there and that it doesn't already exist. In the bottom left corner, we have historical aerial images. And we can see that there's not a building in that image. The bottom left image is taken in 2020 and the top left one is taken in 2021. And in the top right, we have the actual map and how it looks like. And we can also see that in the map, there's not registered a building there. So we can kind of clearly see here that the building was built between 20 and 2021, and someone has forgotten to turn in the notification. Here we have another example of an extension for a building. This one's a little bit harder to find. But for an AI, for humans, when we look at these huge areas, it's really difficult. But for an AI, it looks at every pixel and it can look at them really fast. So they will, if a pixel looks like a building, it will flag it no matter what. And here we have a funny example. It's a house with a grass roof. So if we see at the top left picture here, if we remove the prediction part, we can see that the building, that there is an extension to this building. And we can see in the top right corner that this extension is not registered in the map. We can see in the bottom left in the historical images, we can see that the extension was there in 2012 and in 2010. And the newest one is from 2015. So this one maybe has probably been that humans have overlooked this change for many years in a row, actually. So this is an example of a building extension that an AI has found that humans have not been able to find. Yes. However, the big problem with this is that there was a lot of false positives. The municipality has to go through a lot of these predictions and have to delete a lot of them. So we realized there has to be something that we had overlooked. And if we look at our test area in Kristiansand, we realized where we got really good results. We realized that this is a hugely dense, it's a really dense area. So what we did, we went for another test area in Balsfjord in northern Norway. And this area has a lot more nature, and when we ran the analysis here, we saw that we found 89% of the buildings, but there was 300 false detections. And that's a lot when you have to go through each of them manually and delete them. So we can see that the model struggles with a more diverse area. So for instance, out in the wilderness, out where there's snow, for instance, it thought that the snow was buildings. And since we had the 5% buildings rule, the model hasn't really seen snow before. And also, the images here, they're taken in the spring, so there's not much snow in Norway in general. Some roofs, when the sun reflects on them, such as roofs of greenhouses, they will look really, really, really bright, almost white. And they are buildings, right? So the model has learned that white patches are buildings, and that's probably why when it sees snow out in the wilderness that it thinks it's a building. And we can also see that the model thinks that there is buildings in the ocean because it hasn't seen those before because we had the minimum 5% buildings rule. All right.
Okay, so we created a big training data set from our sample space. We had our 5% building rule to make sure that the data was showing a lot of buildings. And we got a model that was really good in densely populated areas, but not as good in rural areas. So we wanted to continue making things better. So let's look at what we've been doing so far and the problems with it. First of all, we have a limited selection of Norway where we're creating data. And there might be differences between how houses look in the south of Norway, in the north of Norway, and especially the nature is different. We also have a limited variation of nature due to the fact that we're only looking at areas close to buildings. We're also saving a lot of redundant data. So we already have our aerial images in a database. We have our buildings in a database. But then we're creating these images and tiles and saving them. So we're saving the data twice. And the training data that we're producing is also unchangeable data. So if there is a change in our aerial images database or building database, that won't be reflected in our training data unless we produce the training data all over again. If you want to make a change to, for example, the 5% building rule, we would have to create the training data all over again. And this takes time. So there were 3 main challenges that we wanted to solve. We wanted to avoid saving large redundant data sets. We wanted to support adjustable data criteria, not just keep looking at these 5% buildings areas. And we wanted to support adjustable data sources, meaning that we could swap out what data we are connecting to and what the data we're creating training data for. So let's look at the first one. What could we do to avoid saving all of this extra data? Well, if we're not saving it, it means that we have to keep it in memory. And there is one very important requirement that needs to be met. We need to make sure that we can create the training data so fast that the AI model doesn't have to wait for the data. Training a model is already a process that takes time, and we don't want to add to that. So the stream of data has to be as fast or faster than the AI is able to process our data. So we needed some type of benchmark for how fast that was. So we tested on our not so powerful local machine learning computer and found that we had to produce at least 24 images every second. And to give you some idea of how fast that is, 24 images per second is actually the frame rate of a movie streaming in a cinema. So that's what we're aiming for. Okay, so now we could skip our sample space and start looking at all of Norway again. And instead of going through tile for tile, we start just looking at random areas across Norway. And we created what we call a sample generator that produces our data samples. And now the data samples are pushed into a sample queue, and from there into either a training data reservoir or a validation data reservoir. From there, we create batches of data, which we push into a queue of batch data. And last but not least, the data is pushed into the AI model for training. So in order to make this work, we need to run parallel processes. And Python doesn't really have threading, and our goal was to run all of this in Python. We could have done it distributed, but we wanted to see if we could make this run just in Python on one computer because it's cost-effective and very practical, or cost-efficient and practical. So what we could do was to create several Python processes. Each Python process will have its own interpreter, and then you can have these queues with shared memory where the data can flow between those processes. So we run the sample generator in one process, the training data reservoir in a second, the validation in a third, and in reality, these are just Python lists. And the AI model is running in a fourth process. and then the data samples are flowing between these processes with these shared memory queues. So by doing this, we can run all of this in parallel, and we can create the training data while training the model. On to the next challenge.
Yes. So the second challenge we wanted to solve was support for adjustable data criteria. And with these new sample generators, it was quite easy because one sample generator could hold one rule. So we could create a sample generator with a 5% buildings rule. We could create a sample generator with the 20% buildings rule. And we could create one, for instance, with no buildings. And these are then fed into the sample queue as before, and further on to the AI model. But each of these sample generators, they create samples in their own pace. And as we know, as Mathilde mentioned, Norway is made out of 98% nature. So the sample generator for no buildings is going to find samples way faster than the other ones. So we had to kind of limit what they're allowed to put into the sample queue. So we ended up with that 90% of the training data could be from populated areas and 10% could be from unpopulated areas. All right, and the third challenge to solve was support for adjustable data sources. And that was also a lot easier now because now we're streaming the data while we're training. So we could just start a new training, and we could just plug out the buildings database, for instance, and plug in a roads database. And then we can just press play, and the model is now going to detect roads instead of buildings. So great, we got our training rig. We went out to party, probably out until like 4 or 5 a.m. But then when we got back to the office the next day, it was like, wait, not so fast. Because how fast is this data stream really? And when we calculated it, first we have to talk about how the sample generators tries to find these tiles. And for instance, if you have a minimum 5% buildings rule, the sample generators just look and tries to find tiles at random. And so there's a 98% chance that it's going to find a tile with no buildings in it. So it's just going to look, and it's going to, if there's no buildings, it's going to throw it away. And then it's going to look for a new tile, and then a new tile, and then a new tile, and then so on. So it's wasting a lot of time. And when we calculated all of this together, then we find out that it was a whopping 0.22 samples per second. So we needed to come up with some actions of how to fix this.
And at this point, we started doubting our ideas and thinking that maybe this project wasn't such a good idea. But okay, so what actions could we do? Well, we wanted to perform less of the expensive client-server calls. So as Malte just said, we're wasting a lot of time looking at these tiles that doesn't really fit our criteria. And for each tile, we're performing requests to this database in Azure. So we needed to find a faster way to find the areas with buildings. And one a very common analysis to do with geographical data is what's called a buffer analysis. A buffer analysis is that you create a layer that contains the area that is within a certain distance from an object. So if you create a buffer layer of 10 meters from these buildings, it will look like this. So what we did was that we created a buffer analysis, or we performed the buffer analysis for all the buildings in Norway, which gave us a pre-calculated building area. And the image to the right here shows you how this area looks like, and it kind of just looks like a map of Norway. But that's because our buildings are close to the ocean and close to the roads. But this is actually depicting the areas of Norway where there are buildings. So this area was saved to a SQLite database locally, which is small, fast, and self-contained, meaning it has few dependencies. So now, instead of having to perform requests to the database in Azure, we could instead perform a way faster check to the SQLite database and see, are we within or outside the building area? If we're outside of the building area, we know there are no buildings, we don't have to check anything else. we can move on to the next tile. If we're within the building area, we can then move on to checking how many buildings there are by doing requests to the building database. So this makes it much faster. So we had to calculate again, but unfortunately, we're still only at 0.32 samples per second. So we're still way from our goal of 24.
Yes, so the second action we tried was to make more use of the parallel processes that we already were making use of. So each of these sample generators are ran in a separate process. So what we could do is just to scale out horizontally and just add more processes. And the amount of processes, it depends on the CPU on the computer you're working with, of course, but also the amount of allowed database connections. So we found that about 40 parallel sample generators were suitable. So then, again, we celebrated. We went out to party, probably until like 7 a.m. this time. But then when we got to the office the next day, it was like, oh wait, it was still too slow. It was only 5.5 samples per second.
So we needed another action. And this last one is kind of a combination of the most obvious and less obvious thing to do, which is to allow reuse of data. So when you're working with pre-generated training data, you're reusing data all the time. Each epoch, you're letting the model see the same data over and over again to learn from that data. So there's no reason why we shouldn't be able to reuse data in our data stream as well. But we needed to add what we call a minimum level to our data reservoir. And that is to avoid letting the machine learning models see very few samples over and over again in the beginning of training. Otherwise, we would get a problem called overfitting, which is that the model starts memorizing the data that it sees instead of generalizing. But by adding this minimum level in our data reservoir, we could avoid overfitting and just let the model wait a little bit before it started training on the data. So we decided to add a reuse of 10 times. The model gets to see the data 10 times. And after that, we just delete the data. And we always prioritize the least used data. So if the data stream is fast enough, we don't have to reuse the data 10 times. OK, so let's calculate. We had 5.5 samples per second. We allow a reuse of 10 times, which means that we're at 55 samples per second. So it's way faster than the minimum requirement of 24. So we're finally at a place where it's actually fast enough. But we were testing on this small machine, which wasn't really that powerful. And we want to be able to scale it up and use more machine power. And that means that we now can just increase the allowed reuse the data even more than 10 times, and also increase the minimum level to still avoid overfitting. So by doing this, the data stream is even faster, and we can scale the machine that we're training on. OK, so let's summarize. We got our optimal training rig by creating an in-memory stream of data, by using parallel processes in Python, and we made it fast enough by having multiple sample generators, by creating this building buffer area in the local database, and by allowing reuse of data. So we were really happy with the exception of one thing. We have this very defined rules. So we're looking for an area with 5% buildings, 20% buildings. We're saying that we want 10% of our data to be no buildings, and so on. But we don't really know what these numbers should be. What is the optimal split between these different rules, and what should they be? So we did one last thing, which was that we also include data that has low confidence in the AI prediction. So when we're training our model, we're training with data samples, and then we stop and do validation. And during validation, we calculate a confidence score. And the confidence score tells us if the model is really sure of what it's seeing or not. So if the values are close to 1, the model is really sure that it's a building. If it's close to 0, it's very sure that it's not a building. But if the values is around 0.5, 0.6, 0.4, it doesn't really know what it's seeing. It's uncertain of what it is. So it means it has low confidence, and it needs to learn more from that data. So we move that data back into the training data reservoir so that when we start training again, the model gets to see that data and learn from that data. So while we're training, we're continuously improving our selection of training data by letting the model tell us what it hasn't learned yet, which works really well. Okay, so let's look at some results.
Yes, let's look at the fun stuff. So let's look at how we did with the stream data. So if we look at the test area in Balsfjord, these were the old results, and the new results are here. So the true detections went up by 2 percentage points, but more importantly, the false detections went from 300 down to 57. That was a huge improvement. We can see some examples here. The buildings are in pink. We can see that it works quite well, and actually also the shapes, it has gotten really a lot better at detecting the shapes and edges of the buildings. So if we look at a couple of examples here, we have one in the bottom right corner where the new model is detecting this building, but the previous one was not. We have another one where just a small part of the building is detected, but remember that's good enough for us. And then we have an interesting one up here where it was detected correctly before, but is not detected anymore. And this is a greenhouse. And when the sun reflects on this greenhouse, it becomes really white. And you guys remember what I said about snow earlier? This model has probably seen snow, so it has learned that not everything that's white is not a building. So now it doesn't think that, that this greenhouse is a building anymore. We can look at these examples. These are examples where the model is now correctly detecting that they are not buildings, except for the one in the bottom middle there. The old model was actually able to identify that one, but the new one is not. If we look at this one, there is a correctly removal of an extension of a building, and then there is a correct detection of a new building, and then this one is also correctly detecting that there's not a building there. And there's no more buildings in the snow anymore, just like the greenhouse, the snow buildings are now gone. And also the buildings in the ocean are gone. There's now only buildings on land, unfortunately. And there is only, not any buildings here as well in the ocean. Yes, so the improvements have gone from the start of this project for 78% of detected buildings to 93%. But maybe even more importantly, there's 75% less false detections.
Okay, so what are the benefits of this stream data rig? Well, we now get a better general understanding of buildings. And not just buildings, but also nature. We can train on way more training data without having to have extra storage. And the amount of training data that we're now training on is dependent on how long we're training the machine learning model. So the longer it's training, the more data it gets to see. And it's much more easy to change the data sources and create models that detect different things. And we can immediately start training a new model with new data. So how can we take advantage of this new training rig? Well, we can start connecting to different databases. So we're swapping out the buildings database and adding a database with roads, which means that our label is now showing roads instead of buildings, which means that our model is now trying to mimic roads instead of buildings. So we did this and we trained the model for a couple of days and we got these results. So our model is now, or a new model is now able to detect roads or segment roads in aerial images. So this is now a very easy process for us to do. And we can also more easily change out what we're detecting buildings and roads in. So instead of just working with aerial images, we can detect buildings in, for example, height data or laser data, or maybe a combination of the two. And we can train models to detect all different types of objects that are visible in these types of data, like pipes, pools, terraces and stairs, and piers. So these are models that we're creating now due to municipalities that want updated data for this. So in the beginning of the talk, I told you guys that you would learn how to build something illegally without getting detected by an AI. So maybe you have an idea, but our last tip is that maybe you should do something creative with the roof, make it look different than most buildings, or maybe just build in an absurd shape, because otherwise the AI will come and find you. Thanks for listening.